Time varying fields. So far we discussed static electromagnetic field. So in that case both the electric and magnetic field both are time invariant. So in that case the electric field is represented by E of xyz and magnetic field is represented by H of xyz. But in this case of time varying field both are represented by E of xyz of t and magnetic field is represented by H of xyz of t. So in this electric and magnetic field both are time varying. Here the electric field is represented by E of xyz of t and magnetic field is represented by H of xyz of t. So in that case the term t is there in both the electric and magnetic field. And also this electric and magnetic fields are interdependent. But in this case of static electric and magnetic field both are independent, but in this case both the fields are interdependent. And also the time varying fields or waves are due to accelerated charges or time varying currents. So already we know that the electrostatic field, it is due to the stationary charges, and magnetic static field is due to the current charges moving with constant velocity. But in this case of time varying fields or waves, it is due to the time varying currents or accelerated charges. These are some examples for this time varying signals. So first case we know that there is sinusoidal signal, and second is the rectangular signal, and third one is the triangular signal. So all these signals is all the signals are time varying. And also we know that according to Faraday's law, the first law is whenever a conductor cuts the magnetic flux, an EMF is induced in that conductor. And from the second law of Faraday's law, we know that is the magnitude of induced EMF is equal to rate of change of flux linkages. So according to Faraday's law, we can write that the EMF induced is equal to minus of d lambda by dt. So this lambda represents the flux linkages. So we can write that the flux linkages is equal to number of turns into flux. So again we can write that this will be equal to minus of n into d psi by dt. So this is known as transformer and motional EMF. So again this EMF will be equal to minus of d psi by dt, and this is for the one number of turn. If the coil is one number of turn, so this EMF will be equal to minus d psi by dt. So this n equal to 1 here. So this EMF will be equal to minus d psi by dt. And already from the electrostatic field, we already know that the potential or EMF will be equal to the relation between the potential and the electric field intensity, that is E equal to EMF will be equal to integral E dot dl. So again from this equation we can again write that this EMF will be equal to minus d by dt of, instead of this flux we can substitute from the magnetostatic field, the flux is equal to integral B dot ds. So this equation EMF will be, we can write in terms of the electrostatic field and in terms of the magnetostatic field. So we can write this EMF will be equal to, in terms of the electrostatic field, that is line integral E dot dl, but in terms of the magnetostatic field we can write that minus d by dt of integral B dot ds. So this is the induced EMF, VEMF. And this variation of this flux with the time can be caused in three different ways that we can discuss in detail. In the first case, the conductor is, we can take it as stationary. So this conductor is placed in a time varying magnetic field, that is the first case. At the second case, the conductor is varying but the magnetic field kept as stationary. And the third case, both the fields are varying, that is both conductor is varying and also the magnetic field both is varying. So in the first case we know that is the stationary loop in a time varying field. So that is known as, so this is the conductor is stationary, we keep it as stationary, and the magnetic field is varying. And this is an example for the case of the transformer. In the transformer we already know that the conductor is keep it as stationary, but in that case the flux is varying. So this EMF induced in this case is known as transformer EMF. So according to the induced EMF, we already written this equation is in terms of the integral E dot dl, and that also equal to minus of integral dou b by dou t dot ds. So when we apply the Stokes theorem to this equation, we can write that this left hand side becomes, when we apply the Stokes theorem, that according to Stokes theorem, that is to change from the line integral into the surface integral. So we apply Stokes theorem to the left hand side, we will get surface integral of del cross E, that is curl of this vector E, that is del cross E dot ds, and that is equal to the right hand side, both are same, that is minus of integral dou b by dou t dot ds. Now we can when we equating both side, we can write that both the surface integrals are there, both will be cancelled. So the remaining is, inside the integral, the term is del cross E will be equal to minus dou b by dou t, and so this equation is known as Maxwell's third equation for the time varying field. So this is according to Faraday's law. According to Faraday's law, the Maxwell third equation is modified. So this Maxwell third equation for the time varying field is del cross E is equal to minus dou b by. So this equation del cross E is equal to minus dou b by dou t is known as Maxwell's third equation. This is Maxwell's third equation. That is the Maxwell's equation in this for the static electromagnetic field is modified in the for the case of time varying field. So that is according to Faraday's law, the Maxwell third equation is del cross E is equal to minus dou b by dou t. Maxwell's equation is modified for the time varying field. So the second case is the conductor is moving and in a stationary magnetic field. So we know that when a conductor is current conductor is moving in a magnetic field, a force will be exerted on this conductor, and this force equation we know that this force will be equal to Q into U cross B, that we already studied in the basic electrical. Q is the charge and U is the velocity of the moving conductor, and the B is the magnetic field. So from the we already know that electric field intensity E will be equal to force per charge. So this will be equal to this F will be Q into U cross B. This F per Q will be equal to the electric field intensity will be equal to U cross B. And already we know that the induced EMF will be equal to integrating E dot dl. So here it is motional electric field, that is EM dot dl, and this EM we already know that is U cross B. So substitute the value of EM here. So we will get integral U cross B dot dl. Third case, we have both the conductor and magnetic field both are varying. So in that case we can use the equation of both the first two cases, combined equation we can use here. So this in this case with the induced EMF becomes closed integral E dot dl will be equal to minus of integral dou b by dou t dot ds, that is from the first case, then that plus second case, that is integral U cross B dot dl. That is in this case both the first case the stationary loop was conductor was stationary, and second case the the magnetic field was stationary. So in this case, in this equation, both the equations of first two cases we can include it here. So when we take the differential form of this equation, we can write that this del cross E will be equal to minus dou B by dou T plus del cross U cross B. Next is the displacement current. So this displacement current that is derived from the time varying field. So far we discussed the Maxwell's equation for the electrostatic field and is modified according to Faraday's law. So in this case we have to consider the Maxwell fourth equation, that is from the Ampere's law. That is, we know that del cross H is equal to J, that we derived from the Ampere's circuital law. So in that case, when we apply the identity, when we use the identity del dot del cross H is equal to 0, that is divergence of curl of this vector field is 0, that is del dot del cross H is 0. So when we apply this equation to this one also, this del dot J is also will be equal to 0 because del cross H is equal to J. So when we apply this the identity here, del dot del cross H is equal to 0, we can say that del dot J is equal to 0. But we know that according to continuity of current equation, del dot J is equal to minus of dou rho V by dou T. It is not equal to 0. So in order to when we compare these two equations are incompatible. So in order to satisfy the continuity of current equation, we have to add one term to this equation, that is del cross H will be equal to J plus JD. This JD factor we are adding to this equation in order to satisfy the continuity of current equation. So again we are applying the divergence to this curl of this equation. On this left hand side, this becomes del dot del cross H, that is we know that is equal to 0. And when we are applying this divergence to the right hand side also, we will get del dot J plus del dot JD. So we know that this del dot J plus del dot JD, that is equating to 0. So we can write that del dot JD is equal to minus of del dot J. This del dot J is, we know that according to continuity of current equation, it is minus dou rho V by dou T. Substitute this value here. So this becomes minus of minus dou rho V by dou T. So that becomes plus dou rho V by dou T, and that is equal to dou by dou T of, instead of this rho V from the Maxwell first equation, this rho V we know that is del dot D. So this becomes by dou T of del dot D, again that is equal to del dot dou D by dou T. So when we compare these two, we can say that JD is equal to dou D by dou T, and this JD is known as displacement current density, and that is equal to dou D by dou T. D is the electric flux density. So the displacement current density JD is equal to dou D by dou T. Now when we substitute this equation this JD factor into this equation, we can write as del cross H is equal to J plus dou D by dou T. And so the Maxwell fourth equation in the static magnetic field, electric magnetic field, we modified here also for the time varying field. So del cross H is equal to J plus dou D by dou T, and this JD is known as displacement current density. This JD is known as displacement current density. So thus in this case, according to this the Maxwell fourth equation is modified, so we will get del cross H is equal to J plus dou D by dou T. So finally the Maxwell's equation in final form we can write like this for the time varying field. This is for all this equation for the time varying field. The first two equation, there is no change. Del dot D equal to rho V from the Gauss's law and del dot B equal to 0 from the magnetostatics. But the third and fourth equation is modified according to Faraday's law and Ampere's law. That is del cross E equal to minus dou B by dou T, that we got from the Faraday's law, and this is the integral form. And from the Ampere circuit law, we modified the Maxwell fourth equation as del cross H is equal to J plus dou D by dou T.